Hello everyone. We'll now look at section 3.4b, critical points in the first derivative test. So this is sort of an extension onto what we were doing in 3.4a. A lot of the process is the same. You have a couple little extra steps at the end, which we'll get to. First thing we should talk about though is critical values and local maxima and local minima. You see this particular question's asking for those things. So I'm going to start just basically with what a local max and a local min is. If we have a graph that looks, say, something like that, the local max is just a high point of the surroundings. It doesn't have to be the highest point on the graph. In fact, it's usually not. But for instance, in this graph, this little point right here is above what's directly to its left and right. So we call that a local max. Likewise, a local minimum is just lower than its direct surroundings. So this little point right here would be considered a local min, as it's below what's to its left and right. A critical value or a critical point, sometimes they'll call it that. Critical values are simply the x values on a graph which could be local mins or maxes. A more specific definition would be a critical value is an x value such that the derivative either equals 0 or the derivative is undefined and is in the domain of the function. In other words, it could be plugged into the original function. Okay, so let's go ahead and look at what to do here. So I mentioned a lot of this is the same as what we already did in 3.4a. So if I want the critical values, I'm going to take the derivative. So f prime of x equals negative 20x plus 160. Okay. All right, again, the definition I mentioned for critical values is an x value such that the derivative either equals 0 or is undefined. Okay, in this case, we'll just set the derivative equal to 0. We don't have to worry about undefined here, and in fact, you won't have to worry about that part of the definition at all for this semester. That would be like if you have a derivative that has x in the denominator. Okay, we're not going to have anything like that, so all we need to worry about is kind of the first part of that definition. An x value where the derivative equals 0. So I'm just setting the derivative equal to 0 here. And go ahead and solve for x. So 20x equals 160. 160 divided by 20 is going to give us 8. Okay, we called that an x value that had a horizontal tangent in 3.4a. To determine if it's a critical value, we really need to go one step further. And that one step would be, can I take that x value and plug it into the original function and get a number out of it? Well, obviously I can, but we're going to actually need to calculate that value. So let's go ahead and do that. Okay, so I'm going to go ahead and just plug 8 into the original function up there. Not the derivative, the original function. So negative 10 times x squared, x is 8, plus 160x. So x again is 8. And we can go ahead and calculate that. Okay, I got 640. Okay, so what we're saying here, the critical value is going to be 8. That's just the x value. If we wanted to know what the critical point was, the critical point is 8, 640. Okay, so again, if it's asking for the critical values, you're just listing the x value. If it were to ask for the critical point, you'd list the actual point x comma y, 8, 640 in this case. All right, the critical point, 8, 640, is where you can possibly have a local min or a local max. So we're going to do a sign chart for increasing, decreasing, just like we did in 3-4a. Okay, build your number line, put your x value on it, plug in test values into the derivative for each interval that creates. Alright, so in this case I need for the left something between -infinity and 8. Let's pick 0. For the right interval, something bigger than 8. Let's say, I don't know, 10. It's fairly easy to plug in. And go ahead and calculate those in the derivative. Again, the derivative's over here. Okay, so if I plug in 0, -20 times 0 is 0, plus 160 is 160. Okay, so that's a positive number. So that's an increasing interval. If I plug in 10, -20 times 10 is -200, plus 160 is going to give you -40. Okay, so that's a negative number. That means this is a decreasing interval. Alright, in 3-4a, that's really as far as we had to go. We could label our increasing and decreasing intervals. Here, again, you got to go one step further. We're looking for the actual local maxes and local mins. So what I want you to do is think about what's happening here. This left interval is increasing, so it's going up. The right interval is decreasing, so it's going down. So this point right here at 8 is above its surroundings. So that means you must have a local max there. And again, we've already calculated the y value over here for the critical point. So our local max is going to be 8, 640. Okay. We don't have a local min on this graph. Again, to have a local min, you've got to have something going down and then going back up. Then you'd have a local min. But again, we don't have that here. So there's no local min. On Hawks, there's an actual little radio button that you would click that says no local min. Okay, so I'm just writing none on here, but there's an actual little button on the screen where you can just click no local min in Hawks. Okay, so that's your process. This whole process together is called the first derivative test. It's finding the extrema, the local maxes or local mins, on a function. Okay. All right, let's look at another. All right, -9x squared minus 72x plus 8. So, same idea. Derivative. Derivative is -18x minus 72. Set that equals 0. And solve for x. So we'd have 18x equal -72. -72 divided by 18 is going to be -4. Okay. Go ahead and get your y value so you can have your critical point. So you plug -4 into the original function. So -9 times -4 squared minus 72 times -4 plus 8. Okay. And I'm going to go ahead and plug that in my calculator here. Okay, and that comes out to 152. So our critical point is negative 4, comma 152. Alright, for step 1, the critical value, again, that's just the x value, so negative 4. For step 2, you've got to do your sign chart. Okay, negative infinity to infinity. Put your x value, negative 4, on that number line. So we've got two intervals, negative infinity to negative 4, and negative 4 to infinity. Pick a test value in each interval. So for the left here, I'm going to pick negative 5. For the right here, I'm going to pick 0. That's bigger than negative 4. And again, plug those into the derivative over here. Okay. So if we plug in negative 5, we'd have negative 18 times negative 5 minus 72. That would be 18. Okay. Positive number. So we have an increasing interval again. If we plug in 0, negative 18 times 0 is 0. Minus 72 is going to be negative 72. That one's negative, so that's a decreasing interval. Alright, so see what's happening again. This is just like the last one actually. So we've got an increasing interval and then a decreasing interval. So we've got a local max at negative 4. So your local max is negative 4, comma 152. And again, there's no shape like that, so we have no local min. Alright, so fairly straightforward. It's going to be the same process and the rest of the questions. You know, the functions might get a little bit uglier, but it's going to be the same idea on each one. Looking at this one, you have 2x to the 5/4 minus 5x plus 2. But we're going to do the same thing. Okay, derivative. Okay, you're just using your power rule. 2 times 5/4 is 10/4, which is 5/2. Okay, x to the 5/4 minus 1 is 1/4. Derivative of negative 5x is negative 5, and derivative of 2 would be 0. So again, you want to set this equal to 0 and solve for x. Okay. Alright, I'm going to subtract this over. Alright, so your negative signs cancel out on both sides. We need to get rid of the 5/2. So let's multiply each side by 2. So that would leave you 5x to the 1/4 on the left. And if we multiply by 2 on the right, we're going to have negative 10, or excuse me, just 10, because the negative sign's already canceled out. Divide each side by 5. So x to the 1/4 equals 10 over 5 is going to be 2. Alright, so we want to solve this equation with a fractional exponent. So if I want to get rid of the exponent 1/4, I would raise it to the reciprocal of 1/4. So the reciprocal of 1/4 is 4. Or 4 over 1, but we can just use 4. If I do that to the left side, I'm also going to have to do it to the right. So literally what's happening is I have x to the 1/4 that I'm going to raise to 4. And if I do that on the left, I'm also doing that on the right. That leaves you just x on the left, and then 2 to the 4th is 16. Alright, so there's our x value. Now again, just like in the previous questions, we've got to calculate the y value, plug that into the original function to do so. So f of 16 to 2 times 16 to the 5/4 minus 5 times 16 plus 2. Okay, I'm going to plug it in the calculator. 2 times 16 to the 5/4 minus 5 times 16 plus 2, I get negative 14. Okay, so our critical point is 16 comma negative 14. All right, and next comes our number line. So negative infinity to infinity again. Plot your x value on here with 16. All right, so you've got the two intervals again. So for the left interval, you need something less than 16 to go into the derivative. I want to pick 0. For the right interval, you need something bigger than 16. So I'm going to pick, I guess, 17. All right, and again, these are going into the derivative right here. Okay, so if we plug in 0, that's easy enough. 0 raised to anything is 0 times 5/2 is 0. Minus 5 is negative 5. So this is negative, so it's a decreasing interval. 17, I'm just going to plug it in my calculator here. So 5/2 times 17 raised to 1/4 minus 5. Okay, it's an ugly decimal, so it's not exactly equal. It's about 0.08. Okay. So you don't have to be exact there. You basically just want to know, is it positive or negative. 0.08 is a positive number. So this is an increasing interval. All right, so what's happening with the graph? You have a decreasing interval, it's going down, then you have an increasing interval going back up. So we have a low point on the graph. In other words, we have a local min. Okay, and we can answer all our questions from that. So in step 1 up here, your critical values, again, was your x value, so 16. There's no local max on here, so none. And we said we had a local min here at 16. We've already calculated that critical point. It's 16 comma negative 14. Okay. So again, it was a little bit uglier function because you had that fractional exponent, but you know, the work was the same. You did the same process. It's really not any tougher than questions 1 or 2. Okay. All right, I've got one more on here, so let's go down and look at it. Okay, this is a cubic. It's x cubed. Okay, doesn't change what you're going to do though. So let's go ahead and start off the same way. Let's go ahead and get our derivative. So the derivative of 2x cubed is 6x squared. The derivative of 6x squared is 12x. The derivative of negative 90x is negative 90. The derivative of 5 is 0, so that's gone. Set that equal to 0, and we can solve for x. Let's see, 6 goes into 6, 12, and 90, so I'm going to go ahead and factor this 6 out. It's going to leave me an x squared plus 2x minus 15. Okay, and then x squared plus 2x minus 15 factors. Alright, so what do we got to have? We have two numbers that add to 2 and multiply to negative 15. So Looks like positive 5 and negative 3. Okay, use the zero product property to break this apart. So you have 0 equals 6, 0 equals x plus 5, and 0 equals x minus 3. Okay, so 0 equals 6, there's no x to solve for, so we don't get anything from that. For 0 equals x plus 5, x is going to end up being negative 5. For 0 equals x minus 3, x is going to end up being 3. So you actually have two x values this time. Perfectly fine. It's just going to mean you've going to have 3 intervals on the number line when we get to that step. Let's go ahead and get our y values for these. So we'll have our critical points. So for negative 5, again I want to plug into the original function. Okay. I'll go ahead and plug that in here. Two times negative 5 cubed plus 6 times negative 5 squared minus 90 times negative 5 plus 5. I've got 355 for this one. So the critical point is negative 5, comma 355. We've got to do the same thing with the other x value. Plug in 3 into the original and get a y value for it. So 2 times 3 cubed plus 6 times 3 squared minus 90 times 3 plus 5. Alright, so that's negative 157. So our critical point is 3, comma, negative 157. Alright, so we got y values for those, so negative 5 and 3 are both going to be critical values. We can go ahead and list them here. It doesn't matter what order you write them in, just put a comma in between them. If you decide to put 3 comma negative 5 in that fashion, that would be perfectly fine. Just remember, it's just a list of x values, so there's no parentheses around step 1. Okay, step 2 is our local max and min. So let's go ahead and build our number line. There's negative infinity to infinity. We need to plot negative 5 and 3 on this, so make sure you put them in order. Negative 5 should come first, 3 should come second. And you see we have 3 distinct intervals now. Negative infinity to negative 5, negative 5 to 3, and 3 to infinity. So pick a test value in each interval to plug into the derivative. I'm going to pick negative 6 for the far left, I'm going to pick 0 in the middle, and I'm going to pick 4 over here on the right. Alright, let's see what those come out to when we plug into the derivative. Okay. If we plug in negative 6, we'd have 6 54. Okay. So we'd have positive there, so this is increasing. If we plug in 0, we're going to get negative 90. So this is negative, so this is decreasing. And lastly, if we pick 4, we're going to get 54. So this one's positive, so increasing. Okay, so what's happening? You've got a little bit out of room here. Let me get that out of the way. You've got an increasing interval, a decreasing interval, and then another increasing interval. So in this case, we've got a high point right here, so that's a local max. And we've got a low point right here, so that's a local min. Okay, so we have both types of extrema on this graph. Okay, so the local max is at -5, so that critical point was -5, 355. Okay. And the local min was over here at 3, so the critical point was 3, -157 there. So there we go. So again, what we're getting out of this is high points, maxes, and low points, mins, local mins and local maxes for any given function.